Hi math friends, this is AP Calculus section 1.6 day 1. Today we're going to talk about inverse functions. Most of the time when we have functions that relate to variables, and the variables that we commonly use are x and y, but certainly they could be anything, we're looking at specific x values or inputs, and we're finding the y values or the outputs that those x values produce, right? That's the relationship that the function creates between x and y. But what if instead we were looking at y values and we tried to determine the corresponding x values? That would be an inverse function. Before we specifically define what an inverse function is, we need to make sure that we understand a few things. First of all, let's review what one-to-one means. A function f is called a one-to-one function if it never takes on the same x value twice. That is, every x value has a unique y value, right? And we can't have two of the same x values giving us the same y value. For example, when x is 3 and we get 6, if x is 7, we can't also have 6 for the y value if the function is one-to-one. Now, we can still have that for a function, so please don't confuse function with one-to-one function. The rule of a function is just that every x value has one y value. But the rule of one-to-one is that every x has a unique y value. And one of our tests to determine if a function is one-to-one is the horizontal line test. So a function is a one-to-one function only if no horizontal line intersects its graph more than one time. Let's take a look at a few more pieces of information about this. One-to-one functions are important because they are the types of functions that have inverses. So right now, one thing to be thinking about is not every function has an inverse. Only one-to-one functions have inverses. So here's our working definition. If f is a one-to-one function where its domain is A and its range is B, then its inverse function, and we refer to the inverse function with this symbol right here, this f to the negative 1 power, that's how we write f inverse, has domain B and range A, right? So the relationship between a function and its inverse is basically that its domain and its range swap. The x values and the y values switch places. So this definition says that if the function f maps x into y, then f inverse will map y back into x. And as I said before, basically the domain and the range of the original function and its inverse function change places. If we look at example 1, we have 3 different situations here, and we have to decide if the table, the graph, or the given equation represent functions that are one-to-one. So let's look at letter A. We have a table of values, and I am looking at the x's and the y's. Now the first thing I notice is all of my x values are unique, therefore this is a function. But are all of my y values unique? And hopefully you notice right away that when x is 2, my y value, or my f of x, is 2. And when x is 6, again, I get a y value of 2. So that tells me that this is not one-to-one. If we look at letter B, now we have a picture of a graph. So here is where we could use our horizontal line test. So you just have to try to draw a horizontal line. And oh, look at that. I cross it right there, and I cross it again right there. It fails the horizontal line test, so this is also not one-to-one. My third example is cosine x. Now, looking at the equation, you really don't know. You do have to have some prior knowledge about what cosine looks like. But if we were to sketch one period of cosine x, one period is from 0 to 2 pi on the x-axis. And remember, cosine looks like the cup. So there's one period of cosine. Does this pass the horizontal line test? No, it does not. So cosine x is also not 1-to-1. And maybe you remember from pre-calculus that when we were finding the inverse of the cosine function, we had to restrict our domain and just take a tiny little piece of it. So we could say a piece of cosine x does have an inverse, but the entire cosine x, which repeats to infinity in both directions, definitely does not have an inverse. So all three of these were examples of functions that are not 1-to-1 and therefore do not have inverses. Let's take a look at our next example. It says the graph of f is given. Letter A, y is f 1-to-1. Okay, well, since we have a graph, we can use our horizontal line test. And I could draw horizontal lines anywhere that I want, and I only ever cross that pink line one time. So for letter A, I would say f is 1-to-1 because it passes the horizontal line test. And we'll just abbreviate that as HLT. All right, letter B says, what are the domain and range of f inverse? All right, so keep in mind that the graph that we have here on our screen is a graph of f, okay? So first, let's figure out what are the domain and the range of f. So over here, I'll write the domain of f, which again is my x values, right? So it looks like my x values live between here and here. So on the x-axis, that appears to be from -3 to +3. And my range of f is where f lives along my y-axis, from here to here. That appears to be -1 to +3. All right, so this is going to make answering letter B easier because if we want to know the domain and range of f inverse, then basically we're just going to be flip-flopping our domain and our range, right? So then for f inverse, our domain will be -1 to 3, and our f inverse range will be -3 to +3, because we know that a function and its inverse exchange domain and range. It asks us to find f inverse of 2. Okay, well, remember, we have a graph of f, not a graph of f inverse. So f inverse of 2 would be, on our graph, we'd have to look at the point where the value of the function is 2, which is right here, right? That's where the height of our graph is at 2. So f inverse of 2 would be the x value of that point, which would be 0. Because if we have a point 0,2 on f of x, then we would have a point 2,0 on f inverse. So I'm going to say this is because f of 0 equals 2. And then finally, letter D, estimate the value of f inverse of 0. So I look at my curve, and it might help us a little bit if we kind of bold our x-axis here. So when I'm looking at my curve, if I want to know what f inverse of 0 is, then I need to find the location where my curve is crossing the x-axis. So if I look at my graph, that spot appears to be right there. Okay, so I would say f inverse of 0 is approximately, looks like it's about -1.75. Moving on to our next two examples, we are asked to find formulas for the inverse of the functions. So right above it here, we have a nice little table that explains to us the algebraic method for finding the inverse function of a one-to-one function f. Step 1 is we write our function as y equals f of x. Step 2, we're going to solve our equation for x in terms of y, if we can. And then step 3, we express f inverse as a function of x by interchanging x and y. So the resulting equation will be y equals f inverse of x. I think this will make more sense as we go through it. We've definitely done this before, both in Algebra 2 and in pre-calculus. The equations that we worked with may have been a little bit less complicated, but it is the same process. So if we look at example A, the first thing that I am trying to do, it's already written as y equals, right? So I don't have to worry about that. If it had been f of x equals e to the x over 1 plus 2 e to the x, I would have just replaced f of x with y. Okay, so step 1 is done. Step 2, we want to solve the equation for x in terms of y. This one's going to take a little bit of fancy footwork. The first thing that I'm going to do is I'm going to get rid of this 1 plus 2e to the x family in the denominator. So I'm going to multiply both sides by 1 plus 2e to the x power. On the right side, those are going to cancel. So now on the left side, I have 1 plus 2e to the x times y equals e to the x. Remember, I'm trying to get x alone. So I'm going to distribute that y so that I can separate the terms that have x in them. So when I distribute this y, I get y plus 2y e to the x equals e to the x. And then I am going to move the terms that have e to the x, because that's where my variable is, it's the x. I'm going to move both of those terms to the right side of the equal sign. So I'm just going to leave the y here, and I'm going to write this as e to the x minus 2y e to the x. I'm getting closer. Now I'm going to factor out that e to the x. So y equals e to the x times 1 minus 2y. And then hopefully you see where this is going. I can divide by 1 minus 2y. So e to the x would be equal to y over 1 minus 2y. So now I've isolated my term that has x in it. Okay, but if I want to solve for x, because right now x is up in the exponent, remember, and whenever we have a variable in the exponent that we want to get out, we always need to use a log. In this case, the base of our exponent is e, so it makes sense for us to use ln. So right here, I'm going to use ln to rewrite this. Basically, I'm going to take the natural log of both sides of the equation. So natural log of e to the x is equal to natural log of y over 1 minus 2y. And on the left-hand side, the ln and the e, natural log base e of e, that just cancels out. So over here, we get x is equal to the natural log of y over 1 minus 2y. But that's not how we write our answer. Our final answer, remember, is step 3. To express f inverse as a function of x, we need to interchange the x and y. So we just write f inverse of x is equal to the natural log of x over 1 minus 2x. So basically, where my x was, right here on the left-hand side, it's now y, right? Because y is f inverse of x. And then over here where my y's were, those are now x's in my final answer. So this here represents the equation for the inverse of the given function. Letter B, I'm going to give myself a little bit more room. We begin with the function y equals 1 plus the square root of 2 plus 3x. It's already in y equals form, so I don't have to replace f of x with y. I just have to do some algebra. So first I'm going to subtract the 1 to the other side. So now I have y minus 1 equals the square root of 2 plus 3x. And then if I want to undo, again, trying to solve for x, if I want to undo that square root, the next thing that I'm going to need to do is square both sides of this equation to undo that square root. And when I do that, on the left-hand side, I'm just going to leave it right now as the quantity y minus 1 squared. On the right-hand side, the square root and the squared cancel out, so I just have 2 plus 3x. And then again, if I'm trying to solve for x, I would subtract 2. So I would have the y minus 1 quantity squared minus 2 equals 3x. And then the last step, of course, would be to divide by 3. So I'm left with x equals y minus 1 quantity squared minus 2, all of that divided by 3. And I would write my answer. Remember, I'm really thinking now I'm switching x and y. So f inverse of x, which is like y, is equal to x minus 1 squared minus 2 over 3. Okay, now I want to talk about this a little bit further, and actually I should have left myself a little bit space here. One thing I want to say is that this is for values of x that are greater than or equal to 1. We didn't have this issue in the last problem, but we do have this issue here. Okay, and the reason why we need to add this is this makes our inverse 1 to 1. Let's take a look at what this would look like, okay, graphically, because we do know that relationship. Hopefully remember that relationship between a function and its inverse on a graph, that they are reflections of each other over the line y equals x. So if we started with our original function f of x, which is a root function, a positive even root function, okay, and it does have some shifts. So as far as what it looks like, it's just going to look something like this. Okay, this is what we're going to call, this is the picture of f of x, our original function. Okay, and if we look at that line y equals x, which is right there, that's kind of that mirror line, right? Our inverse function, f inverse of x, would have to be a reflection over the x-axis, so it would have to look like this, right? So this would be f inverse of x. Well, this part right here about x being greater than or equal to 1, right here is x equals 1. And so if I were to continue my curve, it would make a parabola, right? Because x minus 1 quantity squared, if I FOILed that out, combined like terms, f inverse is actually the equation for a parabola. But the inverse part of it is just the part where x is greater than or equal to 1. Because if we include the values that are less than 1, we have the other half of the parabola, and notice then that the picture of our inverse would fail the horizontal line test. So that little domain caveat right here that we added, that x has to be greater than or equal to 1, that's what makes our inverse function 1 to 1. Finally, in example 4, it says, given the following graph, sketch the inverse graph on the same coordinate plane. Well, we just discussed this in the last example. To sketch a graph of an inverse function, just reflect the graph f of x over the line y equals x in the coordinate plane. That's easy enough to do. So I'm going to go ahead and sketch in that line y equals x. That's just that diagonal line that crosses right through 0, 0. So to find to sketch a graph of its inverse, I'm just going to reflect the points on the curve over the line. So this point right here will be right here. This point right here will be right there. This point right here is going to stay in the exact same spot, and that point right there is going to stay in the exact same spot because they are on that mirror line y equals x. So there is our graph of our inverse function on the same coordinate plane. Another way to do this, if you don't want to sketch in that line y equals x, is you could identify the ordered pairs. For example, this first ordered pair right now, or right here, is -1, -2. So its partner point should be -2, -1. Because remember, domain and range, just flip-flop with a function and its inverse. So the last two questions ask us basically that question. What are the domain and range of the original function? Well, the domain of f of x is from x equals -1 up to 3, and the range of f of x is from y equals -2 to y equals +3. Sorry, that's a little messy. What are the domain and range of the inverse function? Well, the domain of f inverse is just going to be the range of f, right? So that's going to be -2, 3, and the range of f inverse of x is going to be the domain of f of x, which is -1 to +3.